right, in the last section we'll cover is answering questions about the mean of a population. So this section is devoted to confidence intervals for the population mean. Okay, so what we introduce here is the good old confidence interval. So prior we did confidence interval for P, the population proportion, and now we're going to do confidence interval and also for a difference in population proportions. So now we're going to work on the confidence interval for the population mean mu. So it says, in order to use the confidence interval, okay, in order to use the confidence interval for mu, we need to check the three conditions from the previous section, right? We need random sample, independence, large enough sample size, and of course, if sample without replacement, population size should be at least 10 times larger than sample size. So our estimator here is usually our confidence intervals. It's our estimator, the value, or really the estimate, plus or minus the margin of error. So it just says for a confidence interval, you get your estimator, you add the margin of error, get a number. Then you get your estimate, subtract the margin of error, you get a smaller number. So these two numbers create an interval. They're the walls of our interval of numbers that we believe are plausible. Okay, so remember, margin of error is just some multiplier times the standard error, right? So in the past, this multiplier was z star, right? And it was like, 1.96 or 1.645 or 1.28, right? So the multipliers are commonly known, right? And the standard error, well, that was the standard error or standard deviation of the sampling distribution. Okay, so for the sample mean, the standard error is sigma over root n. But in practice, we usually don't know population standard deviation sigma. Okay, so if we don't know it, well, we don't give up. We just say, okay, I don't know it, so I'm going to have to estimate it with the sample standard deviation s. So sample standard deviation s, remember, that is the typical distance that we should see between any outcome x and the sample mean. Okay, and the sample mean. Okay, so this is the same sample mean that sample standard deviation that we saw earlier in the class. Okay, so here, since we don't know the population standard deviation, what we're going to use is what we call the one sample t interval. So what we get here is the value of our sample mean plus or minus, plus and minus the margin of error. Okay, so here s over root n, that's our standard error, but really we estimated it because we don't know sigma, right? So we plugged in sample standard deviation. Right? Sigma is the Greek letter, and that's the population standard deviation. Okay, and of course here is that since we're using sample standard deviation, we're not going to use a standard normal, or we're not going to use z star. We're going to use t star. Okay, so just know that this t star, it just requires a different table. Okay, but this is just our standard error, and this is still just some multiplier telling us how many standard errors we should include in the margin of error. Okay, so just to give you a feel, the table that we use to recover t star looks like this. And so when we're talking about z star, there was just 4 possible values. So we did like 90, 95, 98, 99% confidence intervals. Okay, but now we have to consider degrees of freedom. Okay, degrees of freedom. So what we do here is our degrees of freedom. So say our sample size, say we want a 99% confidence interval. What is t star? Well, okay, it's 99%, but what I also need to know are the degrees of freedom. So here my sample size was 38, right? Because I did 38 minus 1 is 37. So I need degrees of freedom as well. Okay, because what we get here, this would be my t star value here. Okay, so for a 99% confidence interval for a sample size of 38. So just remember in that previous slide that we saw here, right? Different degrees of freedom, they give you different distributions, right? So the smaller the degrees of freedom, kind of the larger the t star is going to be. Okay, so the difference between t star and z star is that for a 99% confidence interval, T star is always going to be larger than Z star, right? So typically, no matter what, because there's more variation here, right? There's a lot more variation around the mean. What that means is that these T star values, they're larger than Z star values. Okay, and how we find them, it just takes a little bit more work. And you'll find a table similar to this in the appendix A tables in the back of your book. It's A7. Okay, it says T distribution critical values. All right, let's see an example here. So last time we got into like deriving the confidence interval using the sampling distribution for the proportion, right? We really derived using the sampling distribution of the sample proportion. We derived more or less the confidence interval for the sample proportion, for the population proportion. But now let's just jump straight into it, okay? So here it says data on the speed in miles per hour for a random sample of 30 cars traveling on a highway was collected. Okay, the mean speed was 63.3 miles per hour and the standard deviation was 5.3 miles per hour. Okay, so one thing to note right away is that this mean here, this is the sample mean of the 30 cars. And this standard deviation, 5.23, is the standard deviation of the sample of 30 cars. Right, so this is X bar sample mean, and this is S sample standard deviation, and N is our sample size. Okay, so whenever they give you sample size first, then they give you these numbers, then typically these are statistics or estimators, right? So what they want us to do now is find the 95% confidence interval for the mean speed of all cars traveling on the highway. Verify that the necessary conditions hold. I mean, so we can assume, as far as the conditions go, that as far as the conditions, and then we want to interpret the interval, and then we say, is it plausible that the mean speed of cars on the highway is 67 miles per hour? Why or why not? All right, so remember our interval. We're 95% confident that our interval contains the true average speed of 30 cars, right? So anything in our interval is plausible, anything outside we don't believe, right? So after we construct our interval, we're just going to check to see whether this number's in here or not. So I mean, as far as checking our conditions, so as far as checking our conditions, we assume that the sample of cars that they collected is random, and the speed of each car is independent. And we can assume that the population is large, and we're saying at least 300 cars travel on the highway. And the sample is definitely large, right? So it's definitely at least 25 in this case. So the necessary conditions hold. And of course, we're going to use technology to create the interval. Okay, so as you're working on these, we got to be more and more comfortable with StatCrunch. It's very easy to use and very fast. Okay, we can get into interpreting results rather than by hand calculations. Okay, so yeah, you should be using plenty of StatCrunch. So if I were to go into StatCrunch, I just give this here. Okay, so where we would go here, let me just show you where I get this table from. Okay, so let me click on StatCrunch really quick. So you would go to Stat, and we would go to T-stats, okay, because we're using a T confidence interval, and we would go to one sample. And here is with data, and here's with summary. So we're going to use summary because we actually don't have the raw data. We're just given the sample mean, sample standard deviation, and the sample size. So we do with summary. So that's where that table comes from here. Right, so you plug in your sample mean, your sample standard deviation, your sample size, click on confidence interval, whatever level you want, boom, done. Okay, so make sure that you're doing that. Okay, so here, sample mean, I plug in 63.3, sample standard deviation, 5.23, sample size 30. So these are all given in the setup of the problem. And here I want a confidence interval for mu, the population mean, which is 0.95. So here I get this output here. It's saying that your confidence interval, this is your lower limit and your upper limit. So my 95% confidence interval is 61.35 miles per hour to 65.25 miles per hour. Okay, so one thing that's very important is that you can interpret each and every one of these numbers here. Okay, so sample mean, that's the average speed of the 30 cars. Standard error. Okay, so this standard deviation here, this is the typical distance we would expect to see between a single car speed and the average speed of 63.3. Okay, this standard error is the typical distance we should expect to see between the sample mean and the true mean. Okay, so remember, this standard error is saying there's an error. Remember, we're using the sample mean to estimate the population mean, right? So the difference between the population mean and the sample mean, that's the error, right? That's how much our estimator is off by. Okay, so remember, this standard error is going to be smaller than this. So the individual difference is going to be smaller than. Okay. So, I mean, really quickly, just to relate this to all the formulas that we have here, right? So sample mean, that's X bar, that's 63.3 miles per hour. Standard error is our sample standard deviation of the population divided by the square root of n, right? So it was that 5.23 that we were given in the beginning divided by the square root of 30, which gives us that 0.9548, right? So the standard error is the expected difference we should see between the sample mean and the population mean, right? Whereas S is the estimate of the expected difference we should see between a single observation and the population mean. Okay, but of course we had to estimate it. The degrees of freedom here, well, they tell you your sample size, right? So degrees of freedom is always our sample size minus 1. So it's our sample size of 30 cars, a random sample of 30 cars minus 1, which is 29. Okay, now T star. How did they find T star? Well, StatCrunch is always going to be more accurate in finding T star. Okay, the book is terrible in finding accurate values for T star. So, but just for fun, well, actually this value is not too bad. But the T star, so remember, we want T star. It's 95% and degrees of freedom are 29. So in the book, what I do is I go down to degrees of freedom 29, and then I move over to the right until I hit 95%. And when I hit 95%, this is the number that I get. So I'm using the book, the table in your book, right? So that's what they get there. Right, so therefore, in calculating the upper and lower limit, well, they did the sample mean. For the lower limit, they did the sample mean minus this product here, okay, the standard error times T star. So we get 63.3 minus T star times the standard error. So don't forget your order of operations, okay? Make sure to divide this first, then multiply, then subtract off that quantity. Okay, if you subtract these first, yeah, you're wrong. It's completely wrong. Okay, but there's order. Don't forget PEMDAS in your calculations here. Okay, so divide that first, or use that number first, multiply it, then subtract. Okay, we get that number there. Okay, and for upper limit, we do the same thing. Okay, sample mean just plus the margin of error. Okay, the margin of error here. Okay, so there I'm just kind of linking everything together as far as what this output is, because you need to be able to interpret that output. Okay, of course I don't stress calculating these things by hand, but I'm just showing you how it relates to the formulas I showed you earlier. Okay, so as far as in the end, okay, we're 95% confident that the mean speed of cars on the highway is between 61.35 and 65.25 miles per hour. Okay, so we're 95% confident that is the true mean speed of cars on the highway. Okay, so now someone walks in and they say, is 67 a possible mean? And we say, well, no. Okay, so we say since 67 is not in our interval, it is not plausible, it is not a plausible value for the mean speed of cars on the highway. Okay, so if someone who walks in says the average is 67, we would say no, it's not, because that value is not plausible, it's not inside our interval. And we can also conclude that it's less than that, because every single value in this interval is less than 67. Right? So that's what that's indicating us. Now remember, the true interpretation of an interval means, you know, if I were to, I'm really confident that my walls capture the true mean. Right? So So my confidence is in the walls, right? They kind of have it backwards here, but that's okay. I mean, we still get the gist of it, and we still make decisions. Okay. In another example, okay, so here we have a random sample of 35 college students. Was asked how many movies they had seen in the previous month. Okay, so the sample mean was 4.14 movies, with standard deviation 10.02 movies. So n is our sample size, 4.14, that's our sample mean, that's x bar, and 10.02, that's our sample standard deviation s, okay, not sigma. So what we want to do here is construct a 90% confidence interval for the mean number of movies college students see per month. And also we want to know is how will our confidence interval change if we did a 95% versus a 90%? Okay, so everything remains the same. Sample size, everything remains the same, but all we do is change the confidence. Okay, and then we also say, well, what if everything remained the same and all we did was just take a larger sample size? Okay, what do you think would happen? Okay, so we're gonna say, so really what we're talking about is the margin of error. How does margin of error change if we change the confidence level? How does the margin of error change as we increase the sample size? Okay, so if I go back in here, okay, I go back and do the same, I use the same t statistic function in StatCrunch. So I go, my sample mean is 4.14, my sample standard deviation is 10.02, and my sample size is 35. And I want to construct a confidence interval for mu at 90%. Okay, so I change that to 0.90. Okay, so my output is, this is my sample mean, my standard error. So remember, it's 10.02 divided by the square root of 35. That's how they got the standard error. Degrees of freedom was sample size -1, and of course we got my lower and upper limit. So my 90% confidence interval is 1.28 to 7, right? So I'm 90% confident that my interval captures the true mean number of movies watched in the previous month, right? So I can be pretty confident that that true average number is somewhere between 1.28 movies and 7 movies. So once again, just to illustrate, just to link everything together with the formulas that were presented, right? So this here is my sample mean, that's x bar in symbols, and that's 4.14 movies. The standard error here is my sample standard deviation divided by the square root of my sample size. So if we did 10.02 divided by square root of 35, we get this number here, 1.6937. I just rounded there. Okay, and degrees of freedom here, well, that's my sample size -1. Degrees of freedom, df, that's n-1, so 35 minus 1 would be 34. And here's where we have an issue using the book especially, okay, because we want to find T star. We have 90% confidence level and degrees of freedom 34. So if you have the book open and you're going down, it goes 26, 27, 28, 29, 30, 40 degrees of freedom. So it jumps from 30 all the way to 40. Okay, there is no 34. So what do we do? So in this case, you always round down. Okay, so even if it were 36 or 39 or 38, we always round down because we don't want to be overconfident. We rather underestimate than to over. Okay, because we don't want to make a mistake there. But so I mean, that's just the limit of using the book, and that's why we have to use StatCrunch to get more accurate results. But just to give you an idea, T star would be 1.697. Okay, so in there I'm doing 90%, but degrees of freedom 30. Okay, that would be 1.697. Right. So, but StatCrunch, it's using the actual value for degrees of freedom 34. Okay, so if you were to punch this in, we get something slightly different, but they won't be too far off. Okay, if you were to punch this in, it won't be very far off from here. Okay. But the lower limit here, once again, is sample mean minus the margin of error, and upper limit sample mean plus the margin of error. So here we got 4.14 minus this product. So this is my standard error times T star, and I would get my lower limit here. Okay, and then I do the same thing here. So just to note, if when you use these numbers here, they won't be exactly equal to this, but they'll be very close. And that's because if we were to use the book. Okay, but but we're not going to. Okay, we're not going to. They have it there, but we really want to be using StatCrunch. Okay. So going back to here, I mean to the questions now. So we are 90% confident that the mean number of movies seen by college student in a month is between 1.28 and 7.0. And really what we're saying there is we're 90% confident that an interval contains the true mean, okay, of 1.28 movies and 7 movies. So on average, on the average number of movies is between there. So now, okay, here it says a 95% confidence interval would be wider than a 90% confidence interval because 95% confidence interval will have a larger multiplier. And really, I mean, if you think about it, we're increasing our confidence. So we need to back ourselves up by making the interval bigger, right? Because if I'm going to increase my confidence, I got to make the interval bigger. Because think about it. I could say, hey, I'm 100% confidence between negative and infinity. I got a really big interval. I could be very confident, right? But I mean, really, the interval is useless, right? And then if I make the interval very small, I can say, well, hey, well, I'm 20% confident it's between here. Well, I have a very small interval, right? It's very short interval, right? So when you increase your confidence, you're going to increase the size of your interval. Okay, so so as an example here, all I did was 95%. So everything here is the same as before. Everything here is the same. These numbers didn't change, but I'm going to say that they will. Okay, and so oops. So here, if you look here, this is 95%. Okay, so what the only thing that would change is t-star. Okay, and of course here I'm using the book again, but compared to the previous, it's larger. Okay, it's larger. That's the big difference here. When 90%, we were using 1.697, but when we went to 95%, we went from 2.042. So right away, so everything else stayed the same. So what happens is that our margin of error is going to be larger. So therefore, this number is going to be smaller than 1.2761, and this number here is going to be larger than 7.0039, guaranteed. Okay, so increase your confidence, you increase the size of the length of your interval. Okay, now to answer the next question, it says, well, here it's saying if we take a larger sample, standard error would be smaller. This means margin of error would be smaller, and so the interval would be narrower. Okay, so here I revisit the same example, and all I do is just change n. So instead of n being 35, I change it to 100. So right away with standard error, it's going to make it smaller, right? 1.002. Right before, right, with 35, it was 1.69. So right off the bat, the standard error has decreased, right? And that's part of the margin of error, right? So if standard error decreased, guaranteed margin of error decreased. And now, the other thing here is the degrees of freedom. Okay, and obviously I didn't okay, so degrees of freedom here, once again, your book doesn't have 99 degrees of freedom. Okay, so the degrees of freedom here should be 99 because we have a sample size of 100. So T star here, if we're using the book, okay, so unfortunately it doesn't, the next one that's below it here is 1.664. Okay, and this is using the book, okay, which is horrible. Okay, we should just use StatCrunch, okay, but it gives us 99 here. Okay, so so what else would change is this value here, 1.664, 1.664, and 1.664. Okay, so pretty much that changes. This changes. Okay, you gotta get everything color coordinated, right? So it looks cool like a Banksy. All right. So not only does the standard error decrease, but also this critical value also decreases because of the sample size. Okay, so definitely when we increase our sample size, the interval is going to be narrower because this number here is guaranteed to be larger than 1.276, and this upper limit here is guaranteed to be smaller than 7.039 because the margin error is smaller. So I leave it open here. You can go ahead and calculate it to see what those numbers are. Same with the confidence level. You can calculate to see what the numbers are. But once you calculate these, you're going to see you're going to have a wider interval than what this is here, right? And once you calculate these, you're going to see you have a shorter interval than what we have here. Okay. So one more example I just want to show you is that in StatCrunch we can find the confidence interval given the summary statistics, meaning given the sample mean, sample standard deviation, sample size, it can construct the interval for us. But what if we just have the raw data? Okay, what if we just have the raw data? Can we have StatCrunch just find that for us? And so I'm going to revisit this fast food data that we looked at previously. Okay, so I'm going to go back here. Oh, here it is. So I'm going to look at this nutritional data set. So I'm going to open this up here. Okay, so last time we were looking at burgers and the calorie amount in the burgers, and want to know which burger had the smallest calorie count, which one had the largest. I think we found that White Castle had the burger with the smallest amount of calories, but as far as grams per calorie, In-N-Out was the healthiest. But anyways, I just want to build a confidence interval for the calories of the burgers. Okay, so what I'm going to do stat, and I'm going to go to T-stat because it's obviously I don't know the population standard deviation of calories. I don't know, right? Because remember, these burgers, they're a sample of all the possible burgers. So each restaurant, they only gave like a couple burgers, but there's a lot more burgers out there for the restaurants. Okay, so, and one can argue, I mean, are all the burgers, is the total number of burger populations larger than what we see? And but anyways, let me go here. So stat, T-stat, one sample with data. Okay, what summary is like if you're just given the sample mean, sample standard deviation, but if not, we just do with data. So I'm gonna do with data. So I want to do calories. Okay, and the one thing is that, you know, if I just do calories, it's gonna give me the confidence interval of all the calories. But remember, I just want the type which is equal to burger. Okay, so that's what I'm gonna do here. So I'm gonna do that and do that. Okay, and I'm gonna do by type. Okay, that way I get a confidence interval for each type. And I want a confidence interval, let's do 95% confidence interval. Okay, so we go ahead and compute. And here we go. Okay. So what this gives us here, okay, it gives us type, breaded chicken sandwich, burger, chicken nuggets, french fries, grilled chicken sandwich, milkshake. If you look at all the other types, the degrees of freedom, 10, 10, 11, 10, 11, they all have pretty small sample size there, okay? And you look at burger, there's just a lot more burgers than all the other ones. Okay, but for burger, we have a sample mean, which is 620. So that's telling you that for the 68 burgers, the average calorie count was 620 calories, right? And the standard error was 33.36. So that's saying the sample mean of 33.36, the distance between the estimated distance between the sample mean and the true mean of calories, right, is about 33.36 calories. Okay, so remember this 68, this is a sample of all burgers, right? So obviously we sampled these without replacement. So one thing you may argue is the population size, is it at least 680? And so here I'm hoping that it is. I'm hoping that it is. I mean, but if you look at every restaurant, all the different types of hamburgers that they offer, I think maybe we'd be able to get away with this, but it's something that we would check. Okay. Anyway, so it gives you the lower and upper limit. So it's just saying, because remember in this data, they don't give us every single burger from every single restaurant, right? They only give us a selected few. So here, what we're saying is that we're 95% confident that our interval contains the true average calories of the burgers, right? And so every population mean value between 553 and 686, those are plausible values for the true mean number of calories. Okay, so you can even go here and we can do histogram of calories. Let's do this is a histogram of burgers. This is what the histogram of burgers look like. This is the center here, and what this is here is kind of like a QQ plot. Okay, they call it a QQ plot. But sometimes when you actually when you use t, we assume that sometimes we assume the distribution is normal, but population standard deviation is unknown. So what we're doing here is we're comparing like the like first quartile, third quartile, median of the burger calories to the theoretical normal distribution quartiles. And if they're 1-to-1, then it means you have a pretty good normal approximation. So this is a good sign. This is a good sign. But the other thing we have going for us is that sample size is pretty large. Okay, sample size is pretty large, 68. So we could even get away if it was non-normal. But that's just a little something extra there. Okay, but that's just to show you how we in StatCrunch how we would calculate an interval from the data, the raw data itself. Okay, so make sure you know how to do that if asked. But that concludes our lesson for now.